So, hello everyone, let's get started. So today we are not gonna see any new material, but instead we're gonna discuss about the material that we have seen since the start of the lecture. Historically, we have made one of those repeat sessions before exams, which we don't have this semester. But nevertheless, I think it's good to go over the existing material and make sure that you have understood everything, because the things that we do in the following, at least in part, they will be based upon this initial material. So in the following, I'm going to go over the different topics that we have seen in the last lectures, and I'm going to remind you of the things that we have seen about those topics. And I encourage you to ask questions if there's any things that might have remained unclear. And if anyone has questions, please put them in the chat. We can also look again at other slides than the ones that I have here. If there was, for instance, an example in some of the lectures that was unclear to you, then please feel free to ask about it. Once I address the corresponding topic, then we can have a closer look. Okay? Right. All right. So we have essentially discussed about different components in a traditional relational database management system. We always had this architecture slide here, and for most of the components that you see here, we had at least one corresponding lecture. At the beginning, we have started discussing about the interface to the database management system, and that is the SQL language, the structured query language, which has different categories of commands. You have, for instance, the data definition language commands, which essentially allow you to define database schemata. So you can define how the tables look like and what constraints must hold on single tables or between different tables, for instance, primary key constraints and foreign key constraints. Most of the time we have been discussing about the data manipulation language, which after you define the database schema allows you to insert, to delete, to update, and generally to retrieve data in your database. There's also a couple of other categories of commands. We have the transaction control language that we have quickly seen a little bit in the context of transaction processing, which allows you to group different queries into the same transaction. And there's also data control language, which allows you to set access rights. We haven't really discussed about that, but those are the different categories of SQL commands that you have. Now, for the data manipulation language, we have focused a lot about queries that allow you to analyze data. Here, for instance, that's one of the example queries that we have seen. It refers to a database with three relations: students, enrollment information, and courses, where the enrollment links students to specific courses. And then the query that you see below on the slide essentially matches up students with the enrollments that they have registered, and matches that with the course information, filters things down to the CS4320 and CS5320 course groups, the resulting row based on the course name. And then for each of those groups, it calculates a count. It counts the number of rows in that group, and it retrieves the course name, which is the column that characterizes those groups because it appears in the group by statement. So this covers some of the features that we have seen about SQL. We have, for instance, seen many more predicates that we can formulate, for instance, like expressions that allow you to match data against regular expressions. We have seen various aggregation functions that you can use. We have seen additional clauses like the having clause, the order by clause, the limit clause, and we have seen set operations. We have discussed about null values, which essentially represent unknown values. And whenever we evaluate logical expressions in SQL, then the possible results are true and false, but it could also be a null value. We have seen specialized join algorithm, specialized join syntax, like natural joins. We have seen outer joins, and those are some of the features that we have seen. One important feature that we discussed about, and so a couple of examples about, is query nesting, which can be extremely useful in practice when writing SQL queries, in my experience. And with query nesting, you essentially take one SQL query and use it as part in another SQL query. This is what we call nesting. The most complex example that we have seen in this context was probably the one here, which shows you that we can even have multiple levels of nesting. Here again, a query that refers to the university example database. Does anyone still remember what this query was doing, perhaps? I would say this was probably the most difficult SQL query that we have seen in the examples. Right. Let's see, chat. Okay, very good. Yes. So this query essentially asks to retrieve all the courses where we don't have a student for which we don't have an enrollment for the course. So all the courses where not exists a student for which not exists an enrollment for that course. And formulated differently, it means we are seeking those courses, the names of those courses where all students are enrolled. So we cannot find a single student that is not enrolled in the corresponding course. All right. So is there at this point any questions about SQL? So I'm just discuss a high-level overview of the things that we have seen in order to remind you a little bit, and maybe there has been some lingering question that you always had, which hasn't been resolved yet. All right, I guess SQL seems to be working. All right, so that was the interface perspective on the database. In the following lectures, we have been discussing about the database internals, taking essentially a bottom-up approach. We have started our discussion by how the data in the database is actually stored. Now, first of all, we discussed about the hardware on which the data is stored, which is important because the properties of that hardware, they motivate how we store the data. And the first thing that we have seen there, that was this memory hierarchy here, which essentially represents the different levels of a storage in your computer, on which we can store data. And that ranges from layers with a very small capacity, which are, however, very fast to access. For instance, the CPU registers down to levels like a tape backup, which are much slower to access, but on the other side, you get a lot of capacity, and the cost per capacity unit is quite low. So here, essentially, if you go up the memory hierarchy, then you get a faster access. If you go down the memory hierarchy, then you get more capacity. And in database systems, we typically assume that we cannot fit all the data into very high levels of the memory hierarchy. So we have to talk a lot about the cost of moving data between different layers in this memory hierarchy. And this is what the cost model that we've seen for our data processing algorithms is also based upon. Another important property of that hardware is the distinction between volatile and non-volatile hardware. Volatile means essentially that every data that is stored on those devices will be lost if the power drops, if the power is switched off. On the other side, if it is non-volatile, it means that the data persists even if the power suddenly switches off. And this distinction will become extremely important in the context of data recovery, which is the last topic that we have been discussing in the course. So after discussing a bit about the different hardware, we have discussed quickly about different hardware storage, hardware devices to give you an impression for the trade-offs about cost versus capacity, for instance. After that, we have been discussing about how your data is actually stored on those devices. Another important property of many of those storage hardware devices is that it is very inefficient to access single bits and bytes on that hardware. For instance, if you take a hard disk, it has a mechanical part. If you want to read data from a specific location, you have to move the read arm or the read write head physically on the platter. So all of that takes quite a bit of time, and therefore you don't want to read data at a very fine granularity. You want to read it in larger chunks, and this is why in general we assume that all your data is divided into so-called pages, which is the unit at which we retrieve it, for instance, from the hard disk. And a system like Postgres, for instance, typically assigns a couple of kilobytes, something like 8 kilobytes by default to each of those pages. So we have discussed that the data of one relation, which might contain many rows, that is divided into a collection of pages, where each of the pages typically stores multiple rows. Then we still have to think about how we divide the space on one of those pages into slots for storing different rows. And even for each of those rows, we have to think about how we divide the space for the entire row into space for storing specific fields in that row. So in that lecture, I'm not going to go too much into detail, but we have essentially successively divided the storage space until we defined the space for single fields in single rows. And we have seen different variants of that. One particularly important distinction was between rows that always take exactly the same amount of space and rows that where one row in the same relation might take more or less space than another row in the same relation. And depending on which case we are in, we have to use different mechanisms to keep track which bytes belong to which field. Now, with the mechanisms that we've seen initially, we can essentially store one relation as a collection of unsorted rows. The problem is that if you're looking for specific rows, then this representation is not particularly efficient, because in order to search something, you might have to go through every single row in one of those relations. To avoid that, we have seen indexing structures that can be used for more efficient data access. And one of those indexes essentially provides you with a shortcut in order to find those rows that you are looking for. For instance, one of the most popular variants of indexes in practice is based on trees. So those are essentially search trees. And this index always refers to a specific column or a specific combination of columns in a table, which we also call the index search key. And then the index essentially allows you to quickly retrieve rows which have a specific value in the index search key column, or a specific value combination in the composite index search key columns. Some of the indexes also support range predicates, meaning that you can quickly retrieve those rows which satisfy an inequality on the index search key columns. The tree index is one of those, and in practice, one of the most popular variants is the B+ tree index that we have discussed about. Here you see an example index which indexes a relation with students based on the student name. And there's one question in the chat, whether the data access part of the DBMS is just a part of the DBMS that manages all indices. So I mean, one remark already about that, so this architecture that we see here, that is of course highly simplifying. So here, if you look at the actual code of the database system, you will not find specific classes, for instance, for specific components that you see here. So this architecture is to give you an overview of the different aspects of a database management system, and then how that maps to specific parts in a database system implementation. That depends a lot on the system. So with that caveat, I would say that here the data access component that I'm drawing here, it represents essentially all the methods that either create indexes or use indexes for data access. Also methods that don't use indexes for data access, essentially everything which is in charge of either retrieving data or writing data. Okay, and now we also have a question specifically about tree indexes. So here there is a question about clustered indexes versus unclustered indexes and which ones are more efficient. Okay, a couple of questions, great questions. The difference versus like clustered versus unclustered index, it is essentially whether the data that the index refers to is ordered according to the index search key. So in principle, we have seen multiple index versions, depending on whether the index stores in the leaf nodes directly the data or only references to the data. Now, we generally say that an index is clustered if the sort order of the data is consistent with the sort order of the index search key. So basically, if your data is sorted by the index search key. That can be the case if your data is directly found in the leaf nodes of the index. It can also be the case if the leaf nodes only contain references to the data. Now, if you have, for instance, a range scan, where you want to retrieve all the values within a certain range of the index search key. In those cases, it becomes much more efficient if the data that you are ultimately interested in is collocated on consecutive pages. If the sort order of the data is inconsistent with the index search key, then in order to retrieve entries that have the same value for the search key or that they have close by values in a search key, you probably would have to access many different pages in your database, even though you're only interested in reading a few bytes on each of those pages. On the other side, if the index is clustered, we know that those entries which have the same or a similar value for the index search key, they must be close together in the actual data. So in order to read them, we only have to access a few pages next to each other that contain almost exclusively the data that we are interested in. So that is why clustered indexes are typically much more efficient than unclustered indexes. The problem about them is that you can only have one of them per table. So the clustered index refers to the sort order of the data. And I mean, as long as we don't copy all the data, which we typically want to avoid, we have to choose one sort order. And so you can have one clustered index per table. You can have multiple unclustered indexes per table. Access with the clustered index is typically much more efficient. So that is a question that I had a couple of times. So please feel free to ask follow-up questions if that is unclear. But perhaps one of the key points to understand there is really that in order to make an index unclustered or clustered, you don't actually have to change the index itself in some cases. If the index does not contain the data directly, but references to the data, then it would be sufficient to change the sort order of the data in order to turn a clustered into an unclustered index or an unclustered index into a clustered index. Having said that, in practice, what is typical is that you have clustered indexes that integrate the data already in the leaf nodes. In any case, if the data is integrated into the leaf nodes, then there is no ambiguity. It must be a clustered index, because here necessarily the sort order of the data is consistent with the sort order by the index search key. With regards to clustered versus unclustered indexes, does that make sense? Or please feel free to ask follow-up questions. That is typically one of the topics that I get more questions about in the context of indexes. Okay, awesome. All right. And all right, there's one more specific questions about Postgres indexing. I'm going to take that in a second. I just wanted to very quickly wrap up this slide and just remind the people how those indexes are used. So in general, you see that here we have different nodes in the index. Typically in practice, each of those nodes fits exactly on one page. And for the non-leaf nodes in this search key, we essentially have a pass of an index search key value and a reference to a corresponding child node. So if I would be searching for one specific student, let's say we are searching for student Dora, for instance, then I would start the search at the root of the index tree. And here we assume that we have sorted alphabetically by a student name. So if I look at the root node of the index, then essentially P2 will be containing pointers to all students whose name comes before Holly in alphabetical order. And P3 will reference all the students that come starting from Holly and up to Olivia. And P4 will contain everything after Olivia, basically. So here, for Dora, we would be following the pointer to page 2. And here in page 2, we have precisely Dora. So here we take the reference to P11. And now we have reached one of the leaf nodes. On the leaf nodes, we are finding references to the actual data. Here there is Dora, and we see P24, 2, that is what we call a record ID. The first part references a specific page. The second part references a specific record on that page. And so this would be the index version, which contains references to the data. It could also contain the actual data. And one feature of those P+3 indexes is also, you see here, the leaf pages are connected by those red pointers. This is what makes it more efficient to execute range scans where I want to retrieve all the entries whose index search key is between certain value bounds. And here, with those pointers, you can simply follow them along in order to get all the relevant leaf pages. All right. So here there's a question about Postgres indexing in journals. So just to clarify, so some of those methods here, those are things that we haven't directly seen in the course. Depending on the query, it is sometimes sufficient to only look at the index without following references to the data. For instance, if you have something like a count query, you just want to count the number of students whose name is between Felix and Holly, for instance, alphabetically. Then it is actually sufficient to just count the number of references that you find in the index. You don't even need to follow those references to the data. So in those cases, you can use an index-only scan, so you don't even need to look at the data it references. For an index scan, that's not necessarily the case. One thing about indexes is that if you want to, for instance, retrieve, let's say, a non-trivial number of entries from the index, and the index is unclustered, then you might follow references from the index leaf pages, and sometimes those references might actually lead you to the same page again. So in those cases, what you can do is that you essentially create a bitmap, which essentially has bits set to 1 if you need to access specific entries, right? So if you essentially go through the index and create that bitmap, then at the end of it, you haven't really accessed the actual data yet, but you have an overview of which entries you need to retrieve. And so by doing this additional step, you avoid having to access the same reference page twice. And also if you have multiple predicates, multiple predicates in a conjunction on the same table, then you can simply intersect those bitmaps that you have created for each atomic predicate in order to get those entries that satisfy all the predicates. And that is also more efficient than retrieving the entries and then evaluating the other conditions, at least in some cases, right? So a bitmap indexes basically introduces one, bitmap index can essentially introduces one intermediate step where you prepare a bitmap which captures those positions that you're interested in, which makes it, for instance, quite easy to combine multiple predicates, right? So great question. That is already a little bit more advanced, but yes, that is a technique that can have significant impact on performance. Okay. And one question is whether you can have one clustered index and many unclustered indexes on the same table. The answer is yes. So, I mean, if you could have infinitely many clustered indexes on the same table, you would probably want to do that because they're more efficient. But since we have this restriction, yes, we have probably one clustered index and the rest of them are unclustered. Okay, great questions. Now, the second type of indexes that we have been looking at, those are hash indexes. And here we, if you are looking, for instance, for a student with a specific name, then we would first of all evaluate a hash function on the name. And based on the value of that hash function, we would know which hash bucket is interesting. So we would use the index in order to retrieve the content of the hash bucket that is associated with the corresponding hash value. And in that hash bucket, we again either find the actual data, or in this example, we rather find references to the actual data. So a hash index can also be either clustered, or it can also either contain the actual data or also contain references to the actual data. We have seen different versions of hash indexes. here we see an example for the most simple version, which is the static hash index, which doesn't deal particularly well with data insertion. So if you insert more and more data, then at some point your hash buckets, they will overflow. And in the simple version, we just add those overflow pages here, which are linked by the arrows in red. And as you can imagine, if you keep inserting data, then at some point you have some very long chains of overflow pages. And if you are looking for entries with a specific hash value, then you would have to go through all of those overflow pages potentially, and that can be inefficient. So beyond this one, we have seen other more sophisticated hash indexes, extendable hashing, and linear hashing, which either partially or entirely avoid those overflow pages. The principle in any case is that we evaluate the hash function on the key that we are searching for. And since we are using hashing, it makes those hash indexes a little bit more restrictive compared to the tree indexes. They cannot really support conditions of the form one column inequality with some constant. So they can only give you those rows which have exactly a specific value in the search key columns. But unlike tree indexes, they cannot give you rows that satisfy some inequality on the search key columns. All right, and systems like Postgres, for instance, you can often choose which specific type of index you create, and that has some impact on performance and on the types of queries that they support. All right, any lingering questions about indexes before we switch to the next topic? All right. Okay, and there's one question. Okay, if I have a tree index, would I have to re-access pages each time for values on the same page? That is actually a very nice question connecting to the next topic, which is the buffer manager. In practice, it depends. If you're lucky, then you still have cached the page in the buffer manager. So you have to access it, but accessing it is very cheap because it has remained in main memory and you don't need to load it from hard disk again, which is the expensive movement. Right. If we try to calculate cost in cases where we have an unclustered index, in those cases, we typically pessimistically assume that if we read the same page repeatedly, then we are unlucky and haven't cached it, so we have to reread it again and also pay the cost for moving the associated data from hard disk into main memory. So we make that assumption during our cost calculations, but it is a bit simplifying because of the buffer manager component that I wanted to quickly discuss about next. So the buffer manager component is essentially the bridge between a hard disk and main memory, because in order to work with your data, you have to ultimately bring it into main memory and even to the top of this memory hierarchy pyramid to the CPU registers ultimately. But often the most expensive part is moving it from hard disk into main memory. The buffer manager manages the buffer pool, which is essentially the portion of main memory that is reserved for the database management system. And as you can see, it is divided into those so-called frames, where each of the frames can fit one of the pages that we read from hard disk. And the buffer manager essentially gets requests for specific data pages from the higher levels of the database system. And then it either can answer those requests by just referring to some page which is already loaded in main memory in one of those frames, or it has to first load the page from hard disk into one of those frames, which is expensive. So referring to the question on indexing, If we are lucky, then the buffer pool would hold the corresponding page from the index in one of those frames. And if we access it again, it might still be in that frame. The reason why it might not be in that frame anymore is that the buffer pool space is limited. So it can often not fit the entire data set. So the buffer manager tries to be smart about like deciding which of those pages that have been loaded, which ones of them to drop and which of them to keep. But doing this in practice is of course difficult because it requires knowing which data will be accessed next. Okay. Does that make sense for the question on tree indexes? Okay, awesome. Yes, so that is the buffer manager. It tries its best in order to avoid having to reload pages from hard disk, and also keeps track of a little bit of metadata about each of those pages. For instance, like whether the corresponding page has been changed compared to the hard disk version, and that becomes important when deciding which of them to remove and whether we have to first back up data on hard disk or not. Now, the buffer manager essentially forms the bridge between the stored data and the query processor. Query processing essentially has those high-level stages, and you find corresponding components in the architecture slide. If you write an input query, then it is first of all parsed into a tree representation and then simplified using some simple rewrite rules. After that, we have the query optimization process, and here we essentially try to map the input query to the most efficient query plan to execute it. Now, this refers to a key point about SQL, which is that SQL is a declarative language. That means we are not actually telling the database system how a query should be processed. We're just telling the database system which result we want. And then we give absolute freedom to the database system in deciding how it generates that result. And the component which does that is the query optimizer. So based on some cost models, it tries to identify the optimal, the most efficient query plan, which is then forwarded to the execution engine, and then the execution engine executes the different steps in that plan, one after the other one. So this execution engine here processes plans like the ones that you see here, which essentially joins three tables and evaluates a couple of predicates, then counts. So you read those query plans always from the bottom up. At the leaf nodes, you have base tables, and at the root, you have the final query result. Here, each of those inner nodes represents an operation, and those arrows, those tree edges, they represent data flow. So here we have operations that take one operand as input and operations that take two operands as input. For many of those standard operations, such as joins or filter operations, there's actually multiple alternative implementations. So in order to exactly describe what should be executed, the plan needs to contain information that tell the execution engine which implementation to use for specific operations in the plan. So this is what you see here with annotations in red. And there's also some annotations that refer to how data is passed in between different operations. For instance, we might write the result of one operation to hard disk, which means that we materialize it, and then the next operation has to read the result from hard disk again. We might also use pipelining and generate result fragments that are small enough to fit into main memory, and then the next operation can directly start with having only those result fragments. So here we define which implementations to use and how to pass on the results between different operations. For the Operators, we have discussed, for instance, a lot about join operators because the join is often the most expensive operation. We have, for instance, seen the block nested loop join, which is a very flexible implementation that can support arbitrary join conditions, and essentially means that we iterate over blocks in the first and the outer join relation. We load all of those pages into main memory, and then with them in main memory, we iterate over the pages of the other of the so-called inner relation. We always load one page into main memory and we compare all the tuples that we have in main memory to see whether they together satisfy the join condition. If so, we add them to the join result. And after we have treated all blocks, we have generated the full join result. Now, the block nested loop join works for arbitrary join conditions. We have seen more join operators that are more efficient in special cases. So one common case is that your join condition looks like the one that we also see here. We just have the condition that two columns need to have the same value. And in those cases, in practice, you often use, for instance, the hash join, where we, first of all, in the first phase, we partition the input data based on the hash value in the join column. So here we are iterating over the pages of the E for enrollment relation. We load each page and then we calculate the hash value for each tuple. And then we write the corresponding tuple to one of the output buffers depending on the hash value, and we write those output buffers to hard disk. One question that I recently had, just to make sure, about the semantics of tuples and whether that differs from rows in some way. So here in this class, I'm essentially using them interchangeably. So tuple is essentially here used as a synonym basically of row for the purpose of this class. So here the join phase partitions via hash value the first table E and also partitions the second table S. And in the second phase, we have hash partitioned everything. We know that in order for this join condition to be satisfied between two rows from both relations, they first of all must have the same hash value as a precondition. And this is why when doing the join, I can actually focus on pairing up tuples that belong into the same hash bucket. So here I'm iterating over the different hash buckets, and I'm loading into main memory the content of the corresponding hash bucket from one of the two input relations, and then I'm going over the pages for the same hash bucket of the other relation. And because of the particularities of the join condition, I'm guaranteed to generate a full join result here. So those are two of the join algorithms that I have seen. One question that I sometimes get is about the difference between like a hash join and a block, like an index nested loop join that uses a hash index. So please, those are two different things. It's a bit confusing because both are based on hashing, but this hash join here, it doesn't use any pre-existing indexes, but it does the hashing itself in the first phase. Whereas the index nested loop join, where it uses a hash index or a tree index, it always relies on an index that has been generated previously. So those are two different join implementations. One only works if you have an index already. They are somewhat similar because they both are focused on join conditions that correspond to this binary equality type here, but those are different algorithms. You also have seen the sort merge join, which doesn't use hashing, but sorting. That's a general phenomenon a little bit for many of those operator implementations. We had one implementation that uses hashing and one other implementation that uses sorting. And those two join algorithms, sort merge join, hash join, those are some of the most commonly used join algorithms in practice. For instance, Postgres is also implementing. All right, is there any questions on the execution engine at this point? we might not make all components today in the review, but from my side, that's okay. I want to give you the opportunity to ask some lingering questions. So please feel free to ask more questions about the execution engine. All right. Seems execution engine works more or less. Yes. All right. Okay. Good. So if there's no immediate questions at this point, of course, you can always ask questions on Piazza. Also, if some of those things, they make you think and then later you realize that actually something might not yet be clear, then please always feel free to go to Piazza or also to come to one of our office hours. I have mine on Thursdays, for instance. All right. So now the input to the execution engine is a query plan. And for the same query, we typically have many different plan alternatives. So we want to figure out the one that is the cheapest to execute. And that's the job of the query optimizer, which essentially enumerates candidate plans. And it uses a cost model in order to predict the execution cost of those plans. And then it selects the plan that seems to be the cheapest. And that plan is then forwarded to the execution engine. The cost model has the following structure. That is, by the way, also what you have done in one of the homeworks. So here we essentially had asked you to do by hand what the query optimizer typically does automatically for those candidate plans. So cost estimation starts with some statistics about the data, which could be like, for instance, the number of distinct values in specific columns or histograms and so on. And based on that, we first of all estimate the selectivity of all the predicates that appear in the query. And the selectivity, that is just generally the probability that some random row satisfies the predicate. Essentially, the ratio of rows that pass the predicate filter. Now, based on the predicate selectivity values and based on the cardinality of the base tables, I can estimate for a given plan the cardinality of its intermediate results. And that's an important thing to estimate because the processing cost depends a lot on the sizes of the intermediate results that get generated. And based on the number of pages of those intermediate results and based on the cost formulas that we have seen for the different operator implementations, I can estimate the processing cost for a candidate plan, and that gives us an estimate that is used by the optimizer in order to compare alternative plans. Also, the optimizer needs a strategy in order to avoid having to enumerate all possible plan candidates, because that could take actually a long time, because even for moderately large queries, there is way too many alternatives. So that's why we exploit a couple of properties of the query optimization problem in order to reduce work for the optimizer. Many optimizers in practice are using some kind of dynamic programming scheme, for instance, also the Postgres optimizer. And that essentially means that we solve a problem by decomposing it into subproblem. And here in the case of query optimization, we have the problem of figuring out an optimal plan for joining a set of tables. We reduce that problem to the problem of joining some subsets of those tables. And then we compose the optimal plan of joining a set of tables from optimal plans for joining subsets of tables. And here we essentially show that principle for a small query with 3 tables. The optimizer would essentially, first of all, figure out optimal ways of accessing single tables using, for instance, indexes or not using indexes. Then it would use that in order to, so it would essentially compose those optimal access paths for single tables in order to form optimal paths for joining table pairs. And then it would compose those optimal plans for joining table pairs and accessing single tables into an optimal plan for joining those 3 tables. So it essentially calculates optimal plans for joining tables of larger and larger cardinality, reusing the optimal plans for smaller table sets that it generated previously. All right. So now we are pretty much at the time limit. So the next time we're gonna quickly go over the remaining components, the storage manager in particular. And after that, we're gonna start with a new chapter, which is about how we can optimally design a database. Have a nice day, and then I see you again middle of the week.